Okay, so right now we're going to be talking about polynomial functions, their degrees, whether they're odd or even, and how that's going to relate to graphing them. Now, just some quick things right from the start. When a graph is continuous, that means it continues on forever. There are no breaks inside of there. It can be any number of different looking graphs. But the main thing here is that that line is uninterrupted. In non-continuous, there may be some kind of a break in that graph. Or perhaps we're only dealing with the integers. And so we're going to have a graph that only works in whole numbers, in which case it's just going to be a series of dots. In both of those situations, it is not continuous. Now, before we get too far into this discussion, let's even just talk about some of the bare minimum parent functions. So first, we'll have 1 to the power of 1, so that's x. So just x to the power of 1. Now, if I were to draw a graph of just x, well, that's just going to be a line. Now, different functions that involve just x to the power of 1, like a 2x plus 1 or a negative 3x minus 2. Each of them, yeah, they're going to look slightly different, but in the end, all of them are just going to be these straight lines. And that's what we get from x to the power of 1. If we've got x to the power of 2, well, this turns into something a bit more interesting. We've got this graph, which is just x to the power of 2. If we had x plus a 1, then it would be shifted up. Depending on different things that we add to that x squared, it's going to change its look a little bit, but not too much. Now, if I had a negative x squared, it's really just going to be facing down like that. Now, these, of course, are general shapes that are just kind of hinting at what that shape in particular mostly creates. All right, so let's look at x to the power of 3. Now, x to the power of 3 has a bit of this curve. In the negatives, it keeps on going down really quickly. As we get closer to the positives, it starts rising really quickly. If it was a negative x cubed, just kind of reverse that again, just like we did with that x squared. If we're going to have x to the power of 4, well, x to the power of 4, it could look exactly like an x squared. Now, depending on its complexity, we could also get a bit of a w look out of it. And if it was negative, either of those could be reversed. But in the end, one thing I noticed with that is we've got, as this one goes forward, it's going up. As x is going backwards, it's going up. And that's true of either of those, and that's also true of the x squared. Both of them, as we approach the negative infinity, it's going up to positive infinity. As we approach positive infinity, it's going up to infinity. And even with that squiggle there in the middle, the end behavior, what it's doing as our numbers either get really large or really small, is still pretty much the same thing that was happening in the beginning. So now let's look at x to the power of 5. X to the power of 5, it could look even a lot like just our x to the power of 3. Now, depending on its complexity and all the things that we're adding, like a 3x to the power of 4 minus 2x to the power of 2 minus 3x, different things like that, it may have some up and down inside of there. But in the end, once again, we just want to focus in on those main end behaviors. And we see that those are basically the same. Okay, as we're going backwards in the x-axis, both of these are going down. As we're going forwards in the x-axis, both of them are going up. And then if it was a negative x to the power of 5, then just reverse all of that. Now, it's important to note that the x to the power of 3 and the x to the power of 5s, they both have kind of that same behavior in them. The same with x squared and x to the power of 4. Both of them exhibit similar behaviors. And while the graphs can look a little bit different, in the end, as those numbers are either approaching the really high positive numbers or the super, super low negative numbers, the behavior tends to even out and do the exact same thing. All right, so now let's go ahead and look at what we're going to do with properties of even functions. Now, the even functions are going to be symmetric with respect to the y-axis. Okay, and that's what we saw from like an x squared. It was even about that y-axis. The domain is going to be all of the real numbers. Basically, domain is like x. The domain is going to be any number you want. Okay, any number that is in existence, we're going to be able to put into that function. But only the domain. Even notice that small little graph I just drew, we're not going to hit into the negative numbers with our y values. So the range is not going to be all the real numbers because there's going to be some that we never ever touch. Now the parent graph. The parent graphs, when we're talking about even powers, are things like x squared, x to the power of 4, x to the power of 6. These are the parent graphs of even-powered functions. And it's good to note what the parent does because all the children graphs are going to operate in a similar fashion. The parent graph is always going to contain the points of -1, 1, of 0 to 0, and of 1, +1. And that's kind of what we saw with our graphs. They'd start at up here at 1, -1, and then they'd drop down to 0, 0, and then pop back up. Okay, and that's kind of what our even-powered functions will tend to do. The odd power functions are going to be symmetric with respect to the origin. Now, the origin on a graph is right there in the middle. Our odd-powered functions that go like that, while we can't just cut them across the y-axis or x-axis, they do kind of have a rotational symmetry to them. So if I took that chunk and then rotated it 180 degrees, it's going to match on top of that. And that's what we're meaning by symmetric to the origin. Now, both the domain and range in this situation are all the real numbers. In other words, every single y value is possible here. We see that this thing is going to extend into negative infinity, and we also see that it's going to go to positive infinity. So every y value, every x value is possible with the odd power functions. The parent graph is also always going to contain the points. Now, once again, these are just the parent graphs. So x, so that's x to the power of 1, or x to the power of 3, or x to the power of, not 4, that would not be odd, or x to the power of 5. Any of these are going to contain the points 1, -1, -1, 0, 0, and 1, 1. And that kind of shows us what we know. We started out low and we started increasing. Okay, now, our even functions are always going to take on two similar looks. All right, so we have either got them going up. Now, depending on how large they are and complex they are, we may see some up and down things there in the middle, but in the end, it's still going to have that same form of it's going up here and going up here. Now, of course, if you switch that to negative, same thing. Okay, our odd functions, let's do that a little bit better. Our odd functions are going to have this. We started out low at negative infinity. As we moved forward, we then increased to positive infinity. Or the exact opposite. And once again, there could be some up and down right there in the middle, depending on how complex that odd function is. But that end behavior is still going to be the same. So even if you don't want to do all of the graphing of that middle part, you know exactly what the end behavior is just by knowing the greatest power of your first term, the power of your polynomial, essentially. Okay, so let's go on to this graphing. So is this graph even or odd? Well, just looking at it, first thing I'm noticing is that shape that it had. Now that shape, that's one of our odd shapes. Okay, so I know that my greatest power is going to be like an x to the power of 3, an x to the power of 5, an x to the power of 7. It's going to be one of those just by looking at that shape. What are the x-intercepts? Well, so I'm just looking for where x was a 0. So right there, we're going to have x is equal to negative 3. It's one of our x-intercepts. And at x equals 1. Okay? At the x-intercepts, is the function crossing the x-axis or touching? Well, over at the negative 3, we see that it's crossing. Here at the 1, it is only touching. Okay, now this is important for us to be able to write our equation down there. So if it's crossing, one thing that I know from it crossing is that it is going to be an odd power. By virtue of it touching, it's going to be an even power. Now, let's try and see what I mean by that. And we're going to get more into it. We could also replace that power by saying multiplicity. And we'll see what I mean by multiplicity in just a moment. Now, for x equals negative 3 to be a 0 in this situation, we're going to have x plus a 3. So if x was a negative 3, we'd have negative 3 plus 3. That's 0. So this must be one of the factors that builds this equation. Now it was crossing, so we're saying it has an odd power. Now that could mean that we have to the power of 1. Perhaps we saw this happen 3 times. Perhaps we saw it happen a lot more than that. Perhaps we had x plus 3 times x plus 3 times x plus 3 times x plus 3 times x plus 3, and we saw it happen 5 times. Either way, we know that this is just going to be an odd power. I'm going to leave it as it is for right now. Now our next one, x equals 1. So we'd have x minus 1. So 1 minus 1 would be 0. Now this one only touched. It means it's going to have an even power. So it could be to the power of 2, to the power of 4, to the power of 6. In other words, this x minus 1 as a factor either happened 2 times or 4 times or 6 times. And that's what we mean by multiplicity. How many times did we see this x minus 1 repeat as a factor? Now, as I've written it, we've only seen it repeat twice. But it's that twice that is going to cause it only to touch and bounce off rather than to fully cross over. All right, so let's go to our final section. Now here what we're going to do is we are going to identify where are the zeros in each of these functions. So let's start out with just that x minus 2. Well, that means that if x were positive 2, that would be a 0. With x plus 3, Well, that means that x would equal a -3. Now, and then finally, we got x minus a half. So if x equaled 1/2, then that would also be 0. So now that we've done those, let's talk about their multiplicities. Okay, so multiplicities, just how many times they happened. So we see the x minus 2 only happened once. The x minus, or the x plus a 3 happened twice. And the x minus a half happened 4 times. So those are my multiplicities. So at x equals 2, we see it's got one multiplicity that's an odd, so it's going to cross straight over. At the -3, that's twice, so it's only going to bounce off there. And at the 1/2, it's going to bounce off. So if I was creating a graph of this, then we see this is to the power of 7, because we got a 4 plus the 2 plus the 1 degree. And so 7 degrees in total, so it's an odd one. So we're going to start out down here, and it would be going up until we saw the -3 is first, but it's an even one, so it'll only bounce off. Then at the 1/2, but also just bounce off, and then it's going to cross at the 2. So by knowing those numbers, I know the basic shape of what's going to happen here. All right, now this final one, we are going to have to factor it even further than where it's at right now. So first, let's just start out with this one. We need to recognize that that is a sum of cubes. So just looking up the sum of cubes, it is usually written as, so an a cubed plus b cubed, which is then going to equal a plus b multiplied by a squared minus ab plus b squared. All right, and we're just going to plug those numbers in. Now this is just something that you're going to use your reference sheet for. But everywhere where we saw an a, we're just going to put x, and everywhere we see an 8, we're going to put a 2, because 2 times 2 times 2 is what gives us that 8. All right, so we've got the x plus the b times by x squared minus 2x plus b squared. So that's all of my red. We did have that 3 out in front, and now we've got this one right here in green. Now x squared minus 9. I recognize this as a difference of squares, meaning that this is going to be x plus 3 and x minus 3. And that's still squared. All right, now the only thing that may be a bit tricky here now at this point to find the 0 would be this section right here, in which case, if I can't figure out a way to factor it any further than where it's at, because it's a quadratic, I'm probably just going to go ahead and use quadratic formula to find this out. Now, I already know that this is going to give me some imaginary solutions. So due to what we're focused on right now about talking about how these relates to graphs, we're not going to graph the imaginary numbers much. So I'm going to be able to ignore those zeros that I would get from doing the quadratic formula. So I'm going to have a 0 at x equals -2, have a 0 at x equals a negative 3, and at x equals positive 3. So those are going to be my 3 zeros. These two have a multiplicity of 2, and that one just has a multiplicity of 1. All right, so we're going to cross at negative 2, but we're going to bounce at negative 3 and positive 3.